If you look at the universe, gravity seems like the absolute boss. It is the force that pulls stars together, builds galaxies, and keeps your coffee cup resting on the desk right now. It literally shapes space and time itself. Without gravity, the universe would be nothing but an expanding cloud of disorganized gas. But here is the massive, terrifying secret. Gravity is unbelievably weak. Ask yourself this: when you sit down, why don't you fall right through your chair straight to the Earth's core? Gravity is pulling you toward the center of the planet, trying to crush you with the mass of the entire Earth. Yet your chair, which is just wood and plastic, pushes back up and holds you perfectly still. The force holding your chair together, stopping you from falling, is the electromagnetic force that binds atoms and molecules. That simple force is winning the battle against the gravitational pull of the entire planet. Gravity is the weakest of the four fundamental forces in nature. It is so fantastically weak that if we compare it to electromagnetism, the difference is astronomical. If we could put the electromagnetic force into numbers next to gravity, the number for electromagnetism would be a 40-digit number, bigger than the number for gravity. Think of a tiny piece of material, like the atoms in your fingernail. The electromagnetic force between the electrons and protons within those atoms is unbelievably stronger than the gravitational pull between you and the Earth, or even between you and the Sun. This comparison reveals the great paradox of our universe. Why is the force that holds stars together and bends space-time so incredibly feeble? The strength of gravity is something physicists have wondered about for centuries, going all the way back to the 1700s, when thinkers realized that gravity must be a universal pull. Even though gravity is strong enough to keep Earth in orbit around the Sun, it is still so weak that if you were to stand next to the Sun and hold a small magnet, that magnet would be strong enough to resist the gravity of the Sun. If it were to pull on an object of comparable size, the magnet would win. This leads us to a fascinating question: why a tiny magnet beats the entire Earth's gravity? You can do this experiment right now. Pick up a paperclip. Your tiny magnet can easily hold that paperclip up against the entire gravitational pull of our planet. The electromagnetic force generated by that small piece of magnetized metal is greater than the collective gravitational power of 6 septillion kilograms of Earth, the entire mass of our world. The energy holding the atoms of that magnet together is overwhelmingly more effective at exerting influence than the mass of the planet is at pulling the paperclip down. The Earth is struggling just to keep you in your seat. This reality that a trivial human-made device can completely overcome a cosmic force feels wrong, yet it is what defines our physical existence. If gravity is so incredibly weak that a small magnet can defeat the pull of Earth, why gravity still dominates at cosmic scales? The answer lies in two key properties of nature: mass accumulation and electric charge neutrality. The electromagnetic force that powers your magnet is much stronger, but it has one major limitation. It comes in two varieties: positive and negative charges. Normal matter, the atoms that make up you, your chair, and the planet, contains an almost perfectly equal mix of positive charges, protons, and negative charges, electrons. These charges cancel each other out electrically. If your body had even a tiny imbalance of electric charge, the repulsion between you and the Earth would be instantly explosive. Because ordinary matter is electrically neutral, the electromagnetic force cancels itself out almost entirely over large distances. It cannot accumulate force effectively. Gravity, however, only has one sign: attractive mass. There is no such thing as negative mass or anti-gravity in the way we have antimatter or negative charge. Since gravity is purely attractive, every piece of mass in the universe adds its pull to the total without cancellation. When you gather an unimaginable amount of material in one place, like a giant molecular cloud, a star, or a galaxy, all those tiny individual gravitational pulls add up. This accumulation is why gravity, despite its fundamental weakness, becomes the dominant force when structuring the largest objects in the cosmos. Gravity is essentially an extremely persistent, patient collector. Stars form when massive clouds of hydrogen and helium gas collapse together because the local gravity overcomes the gas pressure. Once stars and planets are formed, they orbit each other. Gravity is the architect that organizes everything from solar systems to immense galaxy clusters. The process of forming stars is a constant tug-of-war where pressure, driven by heat and fusion, fights against gravity. In a stable star like our Sun, gravity is balanced by the thermal pressure created by nuclear fusion. But once the nuclear fuel runs out, gravity wins. When a supermassive star exhausts its hydrogen fuel, thermal pressure drops, and the star collapses violently inward under its own weight, leading to a supernova explosion. If the remaining core material exceeds 3 times the mass of the Sun, no known physical force, including the degeneracy pressure that holds up a white dwarf star, can withstand the inward gravitational collapse. Gravity takes the final victory, crushing the material down into an infinitely dense singularity and forming a black hole. Gravity's influence is seen everywhere in the cosmos, acting as the ultimate shaper of celestial objects and the regulator of time itself. First, consider how gravity shapes stars, galaxies, and time. As Einstein correctly described, matter changes the shape of space and time, what we call space-time, and all objects then follow those curves. This simple warping effect is gravity. When a massive star reaches the end of its life, gravity initiates catastrophic collapse, which leads to the formation of incredibly dense remnants. If the collapse halts, a neutron star is formed, an object so dense that a teaspoon of its material would weigh 5 tons. But if the collapse continues, gravity forms a black hole, a region defined only by its extreme space-time curvature. In a black hole, the curvature is so powerful that even light must follow the warped path, trapping it inside a boundary called the event horizon. The black hole itself is defined only by its mass and its spin. This warping of space-time doesn't just affect light, it profoundly affects time, an effect known as time dilation. Near a black hole, gravity slows the passage of time. To an observer far away, time seems to freeze for anything approaching the event horizon. This happens because the distortion of space is so extreme that for everything falling toward the center, the singularity becomes not a place you can avoid, but an inevitable moment in time, the end of its time. On a much larger scale, gravity shapes galaxies through the relentless accretion process. Galaxies like our Milky Way have supermassive black holes at their cores. These black holes grow by matter falling into their gravitational field, forming intensely hot accretion disks. This gravity-driven process is incredibly efficient at converting mass into energy, generating quasars that can outshine all the billions of stars in the host galaxy. The gravitational interaction between these black holes and the surrounding gas is constant, leading to a complex love-hate relationship where the black hole's energy output often regulates the growth of its galaxy by heating and pushing away star-forming fuel. The vast structures of the universe exist because gravity, in its weakness, never lets go of mass, slowly organizing the entire cosmos into clusters and superclusters. The universe's reliance on the feebleness of gravity is necessary for creation itself. The fact that the electromagnetic force is so much stronger than gravity means that matter can exist in stable, complex structures. If gravity were slightly stronger, everything would collapse too quickly. Consider the role of gravity in the formation and regulation of the most powerful structures in the universe, galactic jets. Gravity shapes galaxies not just by pulling them together, but by powering the mechanisms that prevent them from growing too quickly. When matter falls into the gravitational well of a central body, like a supermassive black hole, it gains immense kinetic energy. The swirling material heats up due to friction in the accretion disk, releasing a colossal amount of electromagnetic radiation, X-rays, and radio waves. Some of this energy is channeled into powerful, focused streams of plasma, known as relativistic jets, which shoot out from the poles of the black hole at near the speed of light. These jets are powered by the magnetic fields swirling in the accretion disk, which are twisted and dragged by the rotation of the black hole itself. The sheer amount of energy in these jets can exceed the total gravitational energy holding the stars of the host galaxy together. This process creates a stable cycle. The black hole feeds, the resultant energy pushes away surrounding gas, and this prevents further material from falling in, thus regulating the growth of the galaxy. If gravity were stronger, the black holes would swallow matter too fast, and the universe would be filled with massive, unstable quasars that would incinerate their own galaxies. We can prove the existence of these extreme gravitational objects by observing the stars orbiting them. For example, by tracking the motions of stars near the galactic center over many years, astronomers have precisely calculated the mass of the supermassive black hole Sagittarius A in our Milky Way. This mass concentration, roughly 4 million times that of the Sun, must be confined to an incredibly small area, proving the presence of an extreme gravitational object. The gravitational distortion of space-time is so extreme near these objects that observing the X-rays emitted from the accreting gas allows scientists to estimate how fast the black hole is spinning, based on how much the light is distorted and stretched by the gravity. The simple weakness of gravity is a necessary condition for a stable, long-lived universe that supports complex structures like you and me. To understand this better, we must explore what would happen if gravity were stronger or weaker. If gravity were significantly stronger at the fundamental level, the entire structure of the cosmos would be unstable. 1. Stars would die instantly. Stars form when gravity pulls gas together until fusion starts. If gravity were much stronger, stars would collapse violently and quickly. They would burn their nuclear fuel at a wildly accelerated rate, living extremely short, bright lives before collapsing into black holes or neutron stars. There would not be enough time for stable planetary systems or life to form around them. The universe would have been a fast, chaotic flash of light, followed by universal cold and darkness. 2. Planets would collapse. Even objects like Earth might not be structurally stable. If the gravitational pull were stronger, the electromagnetic forces holding your chair together might lose the battle against the entire planet's pull. If gravity overpowered the forces governing the atomic structure of Earth, the entire planet would collapse under its own weight, leading to massive gravitational runaway and implosion. If gravity was significantly weaker, the universe would struggle to form any structures at all. 1. No stars, no elements. Stars rely on gravity to initiate and sustain the fusion process. If gravity were much weaker, the vast clouds of gas and dust that form stars would never accumulate enough mass to reach the core temperatures required to start fusion. Without stars, the universe would remain a diffuse dark fog of hydrogen and helium, and the heavier elements that make up our bodies like carbon, oxygen, and iron would never be forged. Life, as we know it, would be impossible without the raw materials supplied by stars and supernovae. 2. No galaxies. The organizing force of gravity would be too feeble to hold together the immense collections of mass that form galaxies. The universe would be too expansive and dispersed, lacking the stable, massive systems needed to structure cosmic evolution. Our universe exists in a fragile balance, perfectly tuned by the weakness of gravity. It is only because gravity is so weak relative to the forces holding atoms together that stars can achieve long, stable lifetimes, and complex, self-aware life can evolve on planets that have not collapsed into dense balls of pure nuclear matter. Gravity may dominate the universe on the larger scales, but its mysterious nature on the smaller scales leads to the terrifying realization that we still don't fully understand gravity. This lack of understanding is revealed at the event horizon of a black hole, the place where Einstein's theory of gravity clashes with quantum mechanics, the physics of the very small. Einstein's theory, general relativity, describes gravity as a smooth geometrical curve in space-time. Quantum theory, however, describes everything else, all other forces and particles in discrete quantized packets. These two great pillars of physics cannot be reconciled in the most extreme environment, the black hole singularity, where infinite density is predicted. The quest to unite these two ideas into a unified theory, often called quantum gravity, is driven by the fact that black holes are the only objects in nature where both sets of laws are tested at their absolute limits. This clash gave rise to the black hole information paradox. General relativity suggests that anything falling into a black hole is crushed into the singularity, and all information about it is permanently erased from the rest of the universe. However, quantum theory, through the concept of Hawking radiation, suggests that black holes slowly evaporate by radiating energy and eventually disappear. The paradox is that physics requires information to be conserved. It cannot be destroyed. If a black hole evaporates and disappears, leaving behind only featureless thermal radiation, what happened to the unique information of everything that fell in? If information is truly destroyed, one of the most fundamental laws of the universe is violated. This massive conflict means that one of our foundational assumptions about reality is wrong. The current general consensus among physicists is that information is not erased, but must somehow be preserved in the escaping radiation. The proposed mechanism for how this information is preserved forces scientists to question if space and time themselves are fundamental components of reality, or if they are emergent space-time, meaning they arise from a deeper, more basic physical structure, possibly quantum entanglement. The great cosmic irony is that the immense weakness of gravity, which allowed the universe to organize into stars and galaxies, also creates the greatest mystery in modern physics: the black hole. The black hole acts like a universal key, forcing us to ask sharp, complex questions about the true nature of space, time, and existence. Our limited knowledge of gravity is the most terrifying thing of all, because it hides the answer to how reality fundamentally works. We have seen the paradoxical nature of gravity. It is the weakest force, easily defeated by a magnet, yet it is the supreme architect of the cosmos, dominating every large structure because it accumulates mass without cancellation. This fragile weakness is the exact feature required to create a stable universe where matter doesn't instantly collapse and stars can live long enough to forge the elements necessary for life. If you want to understand space like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. But the places where gravity becomes unimaginably strong at the black hole show us the limits of our knowledge. Our current physics breaks down, yielding mathematical infinities at the singularity and sparking the information paradox that challenges the very foundation of how time and information work. The weakness of gravity allowed us to be here, but its mysteries show us how far we still have to go to truly understand the universe we inhabit. If you're curious about the universe's quiet, dark background and want to explore another massive cosmic mystery related to the absence of energy, click here to Why Space is So Cold video.